Physics JUPEB night class. So let's head into the class immediately. So we'll be starting by explaining what linear momentum is. So by definition, it can be defined as the product of mass and velocity. It's just that simple. The definition for linear momentum, or simply put, momentum, is the product between the mass of an object and the velocity of an object. It's usually represented with the letter P. As you can see here, it's represented with letter P, and it has a formula of P equals mv, where P is representing the linear momentum and m and v are representing mass and velocity, respectively. So it is known to be a vector quantity, meaning, if you remember during our vector class, we said vector quantities are quantities that have magnitude and direction. So it means that this same stuff, the momentum, also has direction. So as much as it has magnitude, it as well has a momentum direction. So these are important things you take like to your mind when you hear the word momentum or linear momentum. First is that it is just the formula is just simple: mass times velocity, just that simple, and it's represented with letter P, or sometimes something that looks like P. Usually it's P. So it's a vector quantity, meaning that it has magnitude and also has direction. So now there is this stuff that they call conservation of momentum. So this law is just similar to the law of conservation of energy. Law of conservation of energy states that energy can neither be created nor destroyed. The same thing with the law of conservation of mass, saying that matter can neither be created nor destroyed, but changed from one form to another. So the same way it applies to the law of conservation of momentum. It said in an isolated system, the total momentum always remains constant. In an isolated system, the total momentum always remains constant. This is the law of conservation of momentum. So for record, you could write it down that the law of momentum states that the total momentum of every isolated system remains constant. And the formula is equals m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. So meaning that on the right-hand side, what you add on the right-hand side, the momentum of a particular object on the right plus the momentum of the particular object on the left, when you do a change in their momentum, it would always be the same. It's always going to be the same. So simply put, the momentum of any isolated system, an isolated system is any system that there is no extra thing coming inside the system. If you've studied chemistry and under thermodynamics, you would remember a portion where they talked about closed system, open system, isolated system. So under isolated system, it's a system where matter does not come in. There is no external thing that is coming inside, and energy also is not coming in. Yeah, sorry, someone is saying something.
Please, I can't see your screen. I'm just joining in. Network have not allowed. Yes, sir. I said good evening. I can't see your screen. I'm just joining in.
Okay, sorry. Seems like probably it's network that is lagging on your end. But can every other person see my screen? Can another person see my screen?
Yeah, I'm just joining in.
Yes, I can see your screen.
Okay, sometimes if you just come into the meeting, sometimes it delays before the screen loads up. So just be patient. So as I was saying, you could just write down, hopefully to come up almost immediately. The law of conservation of momentum states that in an isolated system, the total momentum is always constant. In an isolated system, the total momentum is always constant. And the formula, I said the formula is m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. So now the formula looks like as if it's the same thing as on both sides, but look at it on the left-hand side, we have u, initial velocity, and initial velocity on both sides. So initial velocity of the first object times its mass plus the initial velocity of the second object plus its own mass is equal to the mass of that first object times its final velocity plus the mass of the second object times its final velocity. So what does this law mean in real sense? It's saying that if two objects happen to collide with themselves, there will be no, like, the total velocity at the end would always be equal to the sum of the initial velocities. That is, the momentum of each of the objects before the collision would always be the same after collision. The sum of the momentums of the two objects would always be the same. So now let me bring it like as if I'm trying to simplify it. Let me try simplifying it to something that maybe can be relatable. Just like I said, they're saying something like, if maybe person A is running at maybe 2 meters per second, it's not running meters per second. If person A is moving at 2 meters, okay, let me use momentum so it will be straight for us. I will not be trying to introduce it in a new term. So let's assume person A is moving at a momentum of 10. He has a momentum of 10 kilogram meters per second, and is moving, and another person B is moving at the momentum of 20 meters, 20 kilogram meter per second. These two persons now, if anything happens and they collide, their final momentum, even if one of them seems like as if their momentum is similar to motion, is relating to motion somehow, sometimes. So that's how I was trying to use speed initially. So these two of them, let's assume one person was moving at a higher speed, the other person was moving at a lower speed. At the end, when they collide, the final speed of the first one, of A, plus the final speed of the other, that is the momentum of A plus the momentum of B, would be always equal to their initial one. So now we said at the initial state, the momentum of A was 10. And at the initial state, the momentum of B was 20. So the sum of their momentum is going to be 10 plus 20, that's 30. So now, if at the end of collision, after collision now, the momentum of A now drops to 5, automatically the momentum of B would definitely be 25, because it cannot be higher than or lower than the sum of the previous momentum. I don't know whether I'm communicating.
I did not get it.
Okay, let me just use speed, because I think speed will be more relatable. Assuming two cars were moving at the speed. Maybe one car was moving at 10 meters per second. Then the second car was moving at another speed of 20 meters per second. And both of them had accident and they hit themselves. What would that? They are trying to say that at the end of the whole thing, after the collision, if one of the objects stops, while the other one continues moving, the speed of the one that is continuously moving would be exactly the speed of the total initial speed. That's in the first case, when the both of them they had not had the accident. One of them had 10, the other one had 20. So adding it together, it will give us 30. So the speed after the collision or after the accident can never be anything greater than their individual speed after the accident. If you add it together, it can never be anything greater than that 30 that we got at the beginning. I don't know whether you get it now.
Yes, I understand it now. Thank you.
Yeah, thank you. So that's what the conservation of momentum is trying to explain, that when you see two objects and they have a momentum at the beginning, you can predict the final momentum at the end by just knowing their initial momentum, both of them's initial momentum, and the final momentum of just one. You can be able to tell the momentum of the second one, because it can never be greater than the sum of the initial momentum. So let's move on to the next slide. Let's not dwell much there. So now, we were talking about momentum, and I brought in collision, saying that two things had accident or something like that. So when you talk about momentum, most of the time they always relate it with collision, things hitting themselves and their momentum changing. So now, this under collision now, there are two types of collision. We have elastic collision and inelastic collision. So the difference between these two types of collision is, first, for inelastic collision, is where the first object hits the second object. And when it hits the second object, both of them would stay together and be moving in the same direction. I can see two accidents, like two cars have had accidents. One of them was coming from front, the other one was coming from back. Then as they smash themselves together, both of them started moving. The first car stuck with the second one, and both of them start moving together in one direction. Like what we can see in this diagram here. We have this object A, object B, then both of them, they collided with themselves. Then at the end, both of them, this one stuck to this one, this one glued to this one, and both of them started moving in one direction. That is an example of inelastic collision. That is the final velocity of both of the objects now became the same. So now for elastic collision, now in that case of elastic collision, they said both of them they see experience the same thing, both of them hit themselves. But now, as they hit themselves, one of them bounced off to the left, the other one bounced off to the right. So now this is what they mean. Anytime you hear the word elastic collision, it means after the collision, both objects moved at different direction at different speed. So in elastic collision, after the collision, both objects move at towards different direction at new speeds. Like both of them will have a new speed. But for inelastic collision, after the collision, both objects will move in the same direction and moving with the same speed. I don't know if you get what if you guys are following me. I don't know if you guys are following me.
Yes, sir, we are following
Hello.
you.
Okay, thank you.
Yes, sir,
So
we are
now,
following you.
okay, so now this is the formula for inelastic momentum. So from what I have here, I said inelastic collision, the momentum is conserved. So that's how they say it. You might see it in exam question. They said in inelastic collision, what happens to the momentum and kinetic energy? So for inelastic collision, the momentum is being conserved while the kinetic energy is not conserved. So these are important things that if you're writing in your note, probably you square them out so that you will not mistake them, because these are the distinguishing factors between elastic and inelastic momentum. So if it was me that is writing, I'll probably write it as one side of my notes where I'll square it, put it in a square box so that I will be able to focus on that kind of stuff. Because inelastic momentum, when you hear of inelastic collision, two things should always come to your mind. For inelastic collision, momentum is always conserved, but kinetic energy is not conserved. While for elastic collision, momentum is conserved, the same kinetic energy is also conserved. So that's for inelastic and for elastic collision. So for elastic collision, momentum and kinetic energy is conserved, while for inelastic, momentum is conserved, but kinetic energy is not conserved. So these are the formulas for inelastic collision and elastic collision. So for inelastic collision, this is the formula. The formula is m1u1 plus m2u2. This is the same with the initial general law of conservation of momentum. See it here, we have m1u1, m2u2. That's what we have here. We also have m1u1, m2u2. But now for inelastic, now it's where this thing now change. You now have m1 plus m2 bracket close v. So meaning that the both of them now have the same velocity. There's not like v1 and v2. So v1 is the same thing as v2 for inelastic collision. So that's the explanation that momentum is not conserved. Is conserved, sorry. Momentum is conserved. Why this one? The momentum is also conserved, but kinetic energy is not conserved for for inelastic collision. So see, for kinetic energy for inelastic collision, the formula is normal formula for kinetic energy is half mv squared, or half mass times velocity squared. So for elastic collision, the formula still applies. The kinetic energy for object 1 and the kinetic energy for object 2. Then the kinetic energy for object 1 at the end, kinetic energy for object 2 at the end is going to be, if you add them together, it's always going to be the same. But for inelastic collision, it's not. You can see here I said kinetic energy is not conserved. So I just hope you guys understand what I mean by inelastic collision. Does anybody have any question in regards what we've said so far?
Yes, sir. You said inelastic collision, and here you
Yeah,
said inelastic momentum. Are they the same thing?
inelastic and which one?
There is inelastic collision and inelastic momentum. Are
Okay.
they the same thing?
They don't really have momentum is the same. It's like momentum is the same for both cases. So collision, there are the two types that we have now. We have two types of collision, not two types of momentum. We have two types of collision. So now from these two types of collision now, they are now talking about their momentum and their kinetic energy. So we have two types of collision. We have inelastic and we have elastic. So now they're not talking about two things about each of them. So for inelastic collision, they talked about the momentum and they talked about its kinetic energy. That's what we have here, momentum and kinetic energy. The same thing we had for elastic collision, talking about the momentum and kinetic energy. So for both cases, though their formula is looking different, but for both cases, it is for us to know that it is important that we should know that for both cases, inelastic and elastic, the momentum is always conserved. The momentum is always conserved, meaning that that addition that I told you at the beginning of the lesson, I said if you add the speed and check, if you add the momentum of the first one and the second one at the beginning, if you add it at the end also, it's always be giving you the same answer. So that law still applies for both cases. The momentum is always conserved for both elastic and inelastic. But now, what is different, what distinguishes elastic collision and inelastic collision is the kinetic energy. For inelastic, the kinetic energy is not conserved, while for elastic, the kinetic energy is conserved. I don't know if it's clear.
It's clear, sir. Thank you.
Okay, so let's move on to the next slide. So let's see examples on these stuff. Let's see examples on elastic collision. Let's see examples on elastic collision. So from here, we said two bodies of equal masses collide and exchange velocity. So for elastic collision, when they collide, normally we know that when they collide, both of them at the end will move at different speeds. That's what happens in elastic collision. But in elastic, when they collide, both of them will have the same speed. They will have just one speed and they're moving in the same direction. That's what I said. So now let's see an example under elastic collision. They said two billiard balls collide. Both of them are both balls are ball A and ball B. They have mass of 0.2 kilogram and 0.2 kilogram respectively. But now their speed was ball A was moving at a speed of 3 meters per second at the beginning. Then ball B was at rest. Remember when I said when something is at rest, it means it does not have any speed at all. It does not have any velocity. So ball B was at rest. So its speed was 0. So after collision, ball A stops and ball B moves. So after the collision, ball A stops and ball B moves. So because we know the formula for momentum, formula for conservation of momentum, we can actually tell from the law of momentum, we can tell that no how, the momentum would always be conserved. So let's see how we can prove whether it is true. So from the law of momentum, the formula says that you check m1 times v1, m2 times v2. So that is 0.2 kilogram times its speed plus 0.2 kilogram times its speed. So if you do it here, that's what we have here, 0.2 kilogram times the speed of 3 plus 0.2 kilogram times the speed of this. So now the final velocity, now they said that at the end, the final speed of A becomes 0. So meaning that is 0.2 times A and 0.2 times 3 because the final velocity of B becomes 3. So because if you add this thing, both of them, if you sum both of them, it will give you 0.6. If you do this side will give you, if you do the left hand side will give you 0.6. The right hand side will give you 0.6. So because your right hand side is equal to the left hand side, you can say that the momentum is conserved. Because right hand side is equal to the left hand side, you can say that the momentum is conserved. I don't know if you guys get what I just explained now.
So please, can you come again? Can you come again? Starting from why momentum is conserved.
Okay. From this formula, this example, we're not actually solving anything here. They're just trying to prove that the momentum is conserved for this elastic collision. So now this is what is happening now. We are seeing that they said A had an initial, it has a mass of 0.2, B has a mass of 0.2. So now they said the speed of A is now 3 at the beginning, and the speed of B is 0 at the beginning. While the speed of A at the end is 0 because it stops, and the speed of B is 3 at the end because it stops. So now let's see whether this thing really obeys the law of conservation of momentum. So using the law of conservation of momentum, this is what the law of conservation of momentum says. It says, let me go back to the first place where we saw it. M1 U1 plus M2 U2, that is the mass times the initial velocity, the mass of the second one times the initial velocity is equal to mass of the initial one times the final velocity mass of the second one times the final velocity. So that's what we are doing. So now we have it here. The mass of A times its velocity, that is 3, plus the mass of B times its velocity, that is 0. That's what we have here. You keep that on one side, equals the mass of A now times its final velocity. They say at the end it stops. That is, its final velocity becomes 0, plus the mass of B, 0.2, times its final velocity. Say it moves at 3 meters per second. So its final velocity becomes this. So if you do them individually, it will give us, both sides will be giving us 0.6. So you can press on your calculator and check 0.2 times 3 plus 0.2 times 0, what it gives you. Do the same thing on the other side. You will see that finally the both sides will give you the same answer, 0.6 kilogram meters per second. So that is a proof that since the left-hand side is equal to the right-hand side, it tells that truly momentum is being conserved. Is it clear?
Yes, sir.
Yes,
It's
sir.
clear, sir. Thank you, sir. So, sir,
Okay.
for the same way for the other one, for the kinetic energy, so it will be the same. It will be 0.9 joules at the both sides. So
Yeah,
that
yes, it's the same
justifies
thing on both
that
sides.
kinetic energy is conserved, right?
Yes, if the left-hand side is always equal to the left-hand side, if the left-hand side is equal to the right-hand side, it means that the kinetic energy is conserved as well. So that's what they did here.
Okay, sir.
Kinetic energy is half mv squared, so, or half the speed squared. So if you do it for this side, if you do the kinetic energy on this other side times the kinetic energy of this other side, give you 0.9 on both sides. So because both sides are equal, it can tell you that the kinetic energy is conserved.
Okay, sir. Thank you very much, sir.
Yeah, you're welcome. So let's move on to inelastic collision. So now for inelastic collision, now we know that when we hear inelastic collision, it means that both objects hit themselves. They hit themselves, and when they hit themselves, they like A stayed inside B. Maybe somehow the thing hit with too much force, it got stuck inside B, and both of them started moving in the same direction. So now, when this kind of thing happens, now the formula you can still check for the what they call it, the momentum. If the momentum, it will still give you the same. It will still be proven to be the same. We can try it by ourselves. We can try it individually to try it on our own. Maybe we try using the same formula for conservation of mass of momentum. The final velocity. Let me just calm down. Let's go to the example so you understand what I'm saying clearly. But the law still applies here. So I'll see whether I can explain that law, how to prove the law to you guys, how it applies here. So we have the example here. They say 2 clay balls sticking together, where ball A had a mass of 1 kilogram, moving at 4 meters per second, and ball B had a mass of 1 kilogram, and it moves at 0 meters per second. After collision, they stuck together and move as one mass. So both of them got glued together and they moved as one mass. So now, to use the formula for inelastic collision, we'll use this formula here. The formula that M1U1 plus M2U2 is equal to M1 plus M2 times the velocity. So that is the formula we'll be using. So now looking at the formula now here, we can see it here that the M1 is 1. Its velocity is 4. That's why we have 1 times 4 here. Plus M2 is 1. Its velocity is 0. That's why we have 1 times 0 here. Is equal to the product, the sum of their masses, that is M1 plus M2. That's the mass of A plus mass of B inside here. Then times the final velocity. So now in this case, now they don't know the final velocity, but because of the law of conservation of mass, you can tell the final velocity of the two objects at the end. So now using that formula, we'll be able to get 2. So that if you can now use this same 2, because they're not trying to say that they said that at the end of an inelastic collision, both objects will have the same final velocity. So if we now use this same, because now the final velocity, you can calculate the final velocity as 2. If we now put this same 2 in the first formula, that's this formula here. We put the same 2, that's for V1 will be 2, V2 will be 2. If we put the formula inside here, if we use that V that we've gotten in this formula, it will show us, it will prove that truly the conservation of mass for even inelastic collision is conserved. I don't know whether someone is following me or I'm talking too fast.
Yes, sir. Yes, sir. I'm following.
So too fast, sorry.
Okay.
So you are
Sorry.
fast, but
Sorry. Okay. See what will happen. Everybody, take your probably you have a pen and
Hello,
paper
sir.
beside you. Yeah?
Hello, sir.
Yeah, I
Is
can hear
this
you.
is this the starting point? I've been trying to join since the thing is not connecting.
Okay, it's not really the starting point, but we've not really gone too far. We've not gone too far. So let me just I'll just do a quick summary. Just a quick summary
Okay.
on
Okay.
what has gone on so far for people that just joined in late. So from the beginning, we started with we are talking about momentum and gravitational force and gravitational field. So, and I said that the formula for momentum can be simply called linear momentum. So you can hear it as momentum or linear momentum. And the formula for momentum is mass times velocity. Always, it's always going to be mass times velocity. Mass times velocity. That's momentum is always equal to mass times velocity, and momentum is represented with letter P. So it's represented with letter P and is equal to mass times velocity. So it's a vector quantity. If you can remember what I said about vector quantities, they have magnitude and also they have direction. So with this knowledge now, we then moved on to the conservation of momentum. And I said that this conservation of momentum is a law. It's a law that states that the momentum of any object, any two objects that happens to collide is always going to be constant at the beginning and at the end of the whole process. And I wrote it here. As I said that in an isolated system, the law, I'm writing the law, I wrote the law here that in an isolated system, the total momentum remains constant. So now this formula, the takeaway from this conservation of momentum is this formula is the formula for the conservation of momentum. And I tried giving an example. I said what this conservation of momentum means is if two things hit themselves at the beginning, or if two things were moving at a particular speed, maybe it's a car or trailer. Let me not use something that is bad. Let me not use something that is bad. Let me just use an example that's probably people will relate with. We have maybe a keke and a bicycle. They were moving together. They tried, well, maybe a big car, maybe let's say Toyota car and BMW. They said they want to test which of the cars are strongest. They now said both of them should drive towards themselves and smash themselves together to see which one has power. Like all the stuff that they do with Ram, all this Malu. They will take cow. They'll say one cow, they should fight themselves. Two of them will come and they will run and smash their heads together. So now, if there is the law in physics that says that the speed of the first one and the mass of the first one of the first cow and the speed of the second one and of the second cow and the mass of that second cow, no matter how no matter the speed of both of them came together, no matter their individual speed at the beginning, if they hit together, their momentum at the end would also be the same thing. The sum of their momentum at the beginning would always be the same as the sum of their momentum at the end. That's what the formula is just trying to state, that the sum of momentum of two objects at the beginning of a collision is always going to be the same at the end of the collision. Meaning that if the momentum of A was 2 and the momentum of B was 5 at the beginning, it means that the sum of the momentum of A and B at the beginning is 7. So at the end, if the momentum of B becomes maybe 1, the momentum of A, sorry, momentum of A at the end will be 6, because no matter what, the sum of both momentum must always be equal to the sum of both momentums at the beginning. So that's what this law of conservation of momentum is trying to state. Then I move forward saying that we have collision, two types of collision, because when you're talking about momentum, they always relate it with collision. So and I said that there are two types of collision: elastic collision and inelastic collision. And I said the difference between elastic collision and inelastic collision is in their kinetic energy. So when you talk about collision or elastic collision and inelastic collision, you would always talk about them based on their momentum and kinetic energy. So if you talk about an elastic collision, you talk about its momentum and you talk about its kinetic energy. You talk about inelastic collision, you talk about its momentum and also its kinetic energy. So now, for both elastic and inelastic collision, their momentum is always conserved, meaning it's always the same at the beginning of a process and at the end. It's always conserved. But their kinetic energy, inelastic collision, the kinetic energy is not conserved. While elastic collision, the kinetic energy is conserved at the end. And I said that this is the formula for what I just explained now. So this is the formula for inelastic collision. For inelastic collision, and I explained also that inelastic collision, how to tell that a collision is elastic or a collision is inelastic. For elastic collision, when two objects hit themselves, they will bounce off at different speeds. That's the simple explanation of elastic collision. When two objects hit themselves, they will bounce off at different speed. In other words, their speed might, one of them speed might become slow, the other one speed might become faster. But when they hit together, they will bounce off at different speed and in different directions. That's for elastic. They will bounce off at different speed and different directions. But for inelastic collision, when they collide together, both of them will glue together and they will move in one direction. So that's what we have in this diagram. We have inelastic here. This one coming to hit this one. Both of them collide with themselves. Then they stuck together and start moving in one direction. While in elastic, we have this one coming like this one coming like this. As they hit their heads together, this one went back, this one went back. So this is elastic, while this is inelastic. So this is just a simple explanation of elastic collision and inelastic collision. So the special thing about them now is elastic collision. For elastic collision, their momentum, both of them momentum is conserved. I say momentum is conserved, momentum is conserved. But now here, for inelastic collision, the momentum is not, the kinetic energy, sorry, is not conserved. While here, the kinetic energy is conserved. Kinetic energy is conserved. So that is what we're trying to talk about. That what we've going to talk about so far. So then, and I gave an example that is just trying to prove it, that elastic collision is actually, the momentum is conserved and the kinetic energy is conserved. So from the example, they gave us mass of A, speed of A, mass of B, speed of B at the beginning. Then they gave us final mass of A. They gave us, sorry, speed of B of A at the beginning to be 0, that it stops. Then speed of B at the end to be 3 because it continues moving. And we use it in that formula for conservation of mass. When we applied it, because of the left-hand side gave us the same answer with the right-hand side, we could tell that truly, the momentum was conserved. Then we did the same thing for kinetic energy using the formula here, this formula here. We did the same thing for kinetic energy using this formula here, this one and this one here. So doing that, we solved it here and we got answer that on left-hand side was 0.9, on the right-hand side was the same 0.9. So it's a proof that truly, for elastic collision, both the momentum and the kinetic energy is conserved. So for now, we are now at inelastic collision, and we said they gave two objects, A and B.
Sir, please, the slide you removed. Please,
okay,
the slide you removed before this one. Please let me screenshot.
Okay. So this was where we were before you joined the class. So we are at inelastic collision. I was not trying to tell everybody, okay, let's prove that truly, the kinetic energy of inelastic collision is not conserved. So now, from this example, they said the mass of the first object, mass of A is 1, and the speed of A at the beginning is 1. Mass of B is 1. The speed of B at the beginning is 0. But it did not tell us the speed of both of them at the end, because for inelastic collision, they would stay together. So since they stay together, it means that they will have the same speed. So we then calculated it using the formula for inelastic collision. This formula here, this one here, that says that M1U1 plus M2U2 is equal to M1 plus M2 times V. So the V is what we are looking for, because they believe, according to the inelastic collisions rule, they said the final velocity is always going to be the same for both of them. So now, using with that one, we are able to calculate the V from the formula that we have here. From the solving we have here, we have M1 is 1, V1 and U1 is 4. Here we have M2 is 1, U2 is 0. That's at the beginning. So now at the end, now both of them now stuck together, and we don't know their final speed. So we can now find their final speed by adding their mass from the law of inelastic collision. 1 plus 1 times the velocity. So when we solve it, we are able to get the velocity as 2. We're able to get the velocity as 2. So now I'm not trying to say, let everybody now, we now know that the velocity of M, we now know that U1 is 2. I'm sorry, V1 is 2 and V2 is also 2. So because of that, now I want us to then use our pen and paper to try solving to prove that the kinetic energy is not conserved. It's actually here, but I want us to do it so it will be clear to everyone. So to find out that the kinetic energy is not conserved. So solve this formula using this formula here. This formula here. I want us to use this formula to get the momentum of the kinetic energy of the left-hand side and the kinetic energy of the right-hand side. So I'll be telling you our M1. Write this formula out on your paper. We have half M1 U1 squared plus half M2 U2 squared equals to half M1 V1 squared plus half M2 V2 squared. So now I'm giving from our question, we calculated that from our question we had that our M1 is 1, our U1 is 4, our M2 is 1, our U2 is 0. So write down on your paper, M1 is 1, M2 is 1, U1 is 4, U2 is 0. So now V1 now is 2 on what we calculated. V1 is 2. The same thing with V2 is 2. So now using this formula up here now, let's calculate and see, calculate the right-hand side. Solve this right-hand side and also solve this left-hand side, side by side. If the answer of right-hand side is the same thing with the answer on the left-hand side, then we will know that the momentum, the kinetic energy, is conserved. But if the answer of the right-hand side is different from the answer on the left-hand side, it is proving that the kinetic energy is not conserved. So somebody should solve, you people should solve it and give me the answer for the kinetic energy of left-hand side and the kinetic energy of right-hand side.
What is V1?
V1 is 2 and V2 is 2.
Okay, sir, thank you.
Yeah. So M1 is 1, M2 is 1, U1 is 4, U2 is 0. So V1 is 2, V2 is 2. So solve and tell me what your left-hand side is and what your right-hand side is. So I'll just give maybe 3 minutes or 2 minutes. So someone will give us the answer.
Sorry, please, can you repeat what you said? You said M1 is 1, M2 is what?
M1 is 1, M2 is 1.
Is 1.
Mm-hmm.
U1 is 4. U1 is 4.
U1 is 4. U2 is 0.
V1 is 2. V1 is 2
V1
and V2
V2 is
V1 is 2 and V2 is also 2.
V2.
Because
Okay, thank you.
so V2 is also 2. So both of them have the same speed at the end. Their final velocities are the same. So now let's try to prove whether it will really show that the kinetic energy is not conserved. Because from what our teachers have been telling us, they said kinetic energy for inelastic collision is not conserved. So let's prove it to see whether truly it's not conserved. If it's conserved, the left-hand side would always give us the answer for the right-hand side. And this left-hand side I'm talking about, this side here, these two, adding these two together, that's your left-hand side. Then adding these two together is your right-hand side. So do it and let's see our final answer.
I'm not seeing the words they are showing us. This side and this side. I'm not seeing it.
Are you seeing the small arrow I'm showing? The small arrow that is moving?
No.
Okay, under the last formula that is down, where you have 1/2 M1 U1 raised power 2 plus 1/2 M2 U2 raised power 2 is equal to 1/2 M1 V1 raised power 2 plus 1/2 M2 V2 raised power 2.
Hello, sir.
Yeah, I can hear you.
That's the formula for elastic.
Yeah, that's the formula to check for the conservation, whether kinetic energy is conserved. That's the formula to check whether kinetic energy is conserved.
Okay. If the right hand side is equal to the left hand side, it means
it's
that
conserved.
it's conserved.
Yeah, it's conserved. But if it's not equal, that means it is not conserved. So has anybody gotten the answer?
Yes, sir. The kinetic energy is conserved.
It's conserved. Okay, your right hand side was what? What was your right hand side?
Was 2.
Your left hand side was what?
2.
Okay, I would like someone else to give me their own answer. And you, I would like you to try confirming that everything you did was correct again. So let's see whether anybody would have a different answer or everybody will have the same answer.
Sir, energy is conserved. I got 2 also.
Okay, you got 2 also. Okay. So I'm waiting for just one person should give me another answer, or someone should give me another answer to know whether we are on the same page.
So help me with the parameters. So I didn't get it. I got
Okay,
M11, M2, M11, M21, B1.
yeah,
Is it
V1,
B or B?
V,
V1,
V, V, V. Yeah, V1,
V1,
2,
2,
V1,
V2.
V2, 2. So now, then U1, 4, U2, 0.
Okay.
So now I'll be heading. Does anybody have a different answer from these guys?
No, what I got is that the energy is conserved and is equals to 2.
Okay. So now since 3 persons from the class have given the answer, let's go to see whether it's true. So actually the answer is
I
that
got
the energy is
two
not.
too.
So
It's
the answer
conserved.
is
I
actually
got
that,
two.
okay, it means that somehow we made mistakes somewhere in our solving. The answer is not 2 on both sides. It's not 2. The answer on one side is 8, then the answer on the other side is 4. So let's see how it happens.
Yes. That's what I got. Sorry. Sorry. I got 8 and I got 4 on the other side. Sorry.
So
That's what I
that's
got.
what the answer is. That's what the answer is supposed to be. So let's see how it happens. We have 1 all
So
over
you
2
said the answer is
times
what?
8 on the
Sir.
left hand side. The answer is 8 on the left hand side and 4 on the right hand side. So now let's see how it happens. We have 1 all over 2 times 1 times 4 raised power 2. So let's deal with this
Sir,
one first here.
yeah.
Yeah?
Actually, where we made the mistake was the square. We omitted the square. So that was
That's it.
where we were
Yeah,
making our mistake.
I didn't see the square also.
Yeah, exactly.
Exactly.
So
The
Same here.
square.
it's
Well,
good
it
that
got
we made
8
this
too. It
mistake
got
now.
8 and 4, please.
So it's good that we made this mistake here now, because
Yes, sir.
it's easy for us to omit this kind of things in exams. In your mind,
Yes.
even in the exam, you will see it in the option, you will see the 2 will be there. 2 will be there. And you feel that, wow, at least I should get this one. While there was just a careless error that is not necessarily that you don't know what you're doing, but you know what you're doing, but one slight mistake just made you omit something. So now, those people that made mistake now, it's like as if you've gotten one clear way on how not to make this kind of mistake. Mean next time you're solving this kind of thing, always bring your mind to where you failed it the first time, so that you will not make that same mistake the next time. Anytime you see this kind of formula, always remember to put it 2. if you solve and get your answer, check whether you actually put the 2 at the end. So putting that 2 now, you would find out that on one side you have 8, while on the other side you have 4. Hope everybody got what we did so far.
Yes, sir. Yes, sir.
Yes, I think so.
Okay. So
Yes, sir.
So now let's move on to, that's a proof that truly inelastic. As mean you people's answer were correct. The people that said 2, as mean the answers were correct. That means I would have sent a message to United Nations and tell them that some of our students here, they've proven the law of conservation of momentum wrong, but we made mistakes. So that means we're not proving anything wrong. So let's move on. So now real life application, as I was saying, this conservation of momentum, it actually applies in cases of accident and also in cases of gunshots, where you shoot something and the person you shot, the bullet will stick into the person's body, and the person will move with a particular speed backward, depending on the speed and mass of the object. So that's just all those incidents where you have 2 things colliding with themselves, and one thing, either they would move in elastic collision pattern or inelastic collision pattern. So these are the places that this idea can help in some level of engineering. There's how they can apply these things. There's how they can apply this thing, and they'll be able to get profitable results. They'll be able to get profitable results such that they can know that, okay, if a particular car hits a particular building, because of the mass of the building, they can be able to tell that, okay, if this thing hits the building will not collapse. Instead, what will happen is that the car will stop. Both of them velocity will become 0. They will know the kind of mass of the object that you can set that will turn the velocity to 0. Because if not, it would pull the building down. So all these ideas, the engineers, they always take all these into consideration when they are doing their calculations. So such that they can be able to create stuff that will be able to last for a while. Even in the creation of rockets, they make use of this law in a way, in combination with the Newton's 3rd law, but we'll get there later on. Let's move on to what we have next. The topic was on momentum and gravitational field. So now we've gone to the portion of gravitational field now. So when we talk about gravitational force, everybody knows, most of us know what gravitational force is. That is the force that acts on a body as a result of it being present inside the Earth. It's the force that the Earth exerts on everybody that is inside the Earth. So it's a downward force that the Earth exerts on everybody. That's what gravity is. It's a downward force that the Earth exerts on every object that is inside it or close to it. So that's what gravitational force is. So in real sense, in reality, what actually makes every object can generate a particular every object can generate its own gravity. But now, for the gravity to be significant enough, the object needs to be very, very big. So that is the reason why we don't know our individual force of gravity that we are exerting to people that are around us. So if we can grow ourselves very big to the point that we can bend space and time, we can be able to cause gravity. We can be able to generate a force of gravity around us that anybody that comes near us will come and meet us. Like anybody that comes close to us would always fall into us or come towards us. So I guess this is the ideology that probably some people say in some kind of metaphysical stuff, the way they'll say, if you can make your energy strong enough, things will gravitate towards you, law of attraction and all those kind of stuff. So it's based on some of all these basic laws of physics and life. So generally, how gravity happens is when an object is very big, very, very big, it bends space and time. And as it bends space and time, things that are now around it would then start rolling towards it. It's just like as if you had a bed sheet, like a bedspread. The bedspread is space and time. Someone holds it at one end, one person holds another end, 4 people hold the bedspread at 4 ends and stretch it out completely. If you drop a grain of sand on top of that that bedspread, the bedspread will not sink inside. It will not go inside. And it's not exactly, it will not go inside. But when you carry something that is as heavy as maybe a pressing iron and put on top of that spread wrapper or something like that, when you put that type of object like a pressing iron, it will sink what they call it, this wrapper. And when it sinks that wrapper, it will bend that wrapper inside. So now if you drop anything close to the ion inside that wrapper, anything close to that ion inside that wrapper, that thing will roll towards the ion. I don't know whether you guys are understanding what I'm trying to explain. Are you guys following me?
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
So this is how
Yes, sir, we are
gravity,
following
this
you.
is how this is how the earth generates gravity. I'm just trying to give you people an overview. Probably for some people, I don't know where you guys will probably go on in your studies, but I'm trying to bring an idea about what gravity is. So it's just like as if you have a wrapper, a short wrapper, or you have a big wrapper, then someone drags it, people drag it, they spread it out on the air. One person holds on one end, one person holds on another end, and they hold it on the air, they suspend it on the air, holding one end. So it will stay on the air stretched, completely stretched. So now if you drop small items on top of it, they will not really sink that wrapper, except you carry something that is very big. Even if they sink the wrapper, they might just think it's very small. And even if you drop another object near them, that object will not roll towards them. But when you carry something that is very big, something as big as maybe an iron or a pressing iron or even a heavy stuff, something that is very big and heavy, drop it at any point on that wrapper. Anything that is close to that thing will roll towards that place, that depth that thing creates. So that depression that thing creates, that's what actually happens with our Earth's gravity. Our Earth is very big and it is resting on top of a plane that is called time and space. So because it's very big, it bends time and space, making it be that anything that is around the Earth would drift towards the Earth, would want to enter into the Earth. So this is the idea of gravity. So, but this one is not what we are trying to teach here. So this is now Newton from his own study, he then generated what we know as the law of gravity, which is trying to talk about gravitational force. He's trying to explain how gravitational force happens. So according to Newton's law of gravity, he says every object in the universe attracts every other object with a force that is directly proportional to the products of their masses and inversely proportional to the square of the distance between them. So this law is just simply this representation here, that the force, you say every object in the universe attracts every other object with a force, that is the force here, F, which is equal to, or which is directly proportional to the product of both of them's masses. So now we have object A and object B. The force that object A will exert on object B, the gravitational pull that object A would exert on object B, would be equal to the product of, will be proportional to the product of their masses, both object A and object B, and inversely proportional to the square of the distance between object A and object B. So that's what this Newton's law of gravity states. So the constant of proportionality is G. So now the formula now is just simply giving us F is equal to G times M1, M2 all over R squared. G times M1, M2 all over R squared. So that's the formula for Newton's law of gravity. It's important that we should know this formula because I've seen in several cases where in exam they'll tell you which of these options indicates the Newton's law of gravity. It comes out very well, and it's actually a simple law. Just F, the gravitational force is always equal to the constant G. This is not acceleration due to gravity. This is a constant G, a special constant, gravitational constant G into bracket M1 times M2 bracket close all over R squared. So now these parameters, what they mean is F is the force of gravity, gravitational force, not acceleration due to gravity. There's acceleration due to gravity. There is gravitational constant. But here we're not talking about acceleration due to gravity. We're talking about gravitational constant, gravitational force, the masses of the object, and the distance between these two objects. So we have one object on one spot, another object on another spot. Then we're now trying to see the force of gravity that one of the objects exerts on the other object. So to get that force of gravity, you need to first measure the distance between both objects and know the masses of both objects. Then there's a general constant that you can multiply with this that will give you the force of each object on each other. So this is the formula for Newton's law of gravity. So the constant G, the gravitational constant, is a constant and its value is 6.67 times 10 raised to the power of minus 11. 6.67 times 10 raised to the power of minus 11. 6.67 times 10 raised to the power of minus 11. Memorize this stuff. 6.67 times 10 raised to the power of minus 11 because it comes out in exam. I've seen it in exams, in exam questions. Even if you enter university in your year 2 physics. Okay, you guys probably will be entering 200 level, but people that will be in physics, these formulas will be coming out. So the formula, the constant 6.67 times 10 raised power of minus 11. This is a gravitational constant, and you should memorize it. So then M1 is the mass of the first object, M2 is mass of the second object, then R is the distance between M1 and M2. So now let's go on to calculations. Let's see some example of how questions come out under this topic. So now we have a question that says two masses, M1 being 5 kilogram, M2 being 10 kilogram, are placed 2 meters apart in a vacuum. Calculate the gravitational force between them, taking that the gravitational constant is this. So this is the formula. This is the constant I said you should memorize. So to calculate this thing is just very simple. I think this is one of those simple solvings in physics.
The example, we can't see it on the screen.
Can you see it now? Can everybody see my screen now?
Though.
Okay, I think probably sometimes if network is glitching, it will delay your screen from responding immediately. So probably it's network at your end. So just, I apologize for that inconvenience. So this is the formula. The formula state, the equation states that two masses, M1 equals 5 kilogram, M2 equals 10 kilogram, are placed 2 meters apart. That is the distance between M1 and M2 is 2 meters in a vacuum. Calculate the gravitational force between them. So they're asking us to find the F. They're trying to tell us to find F, and the gravitational constant they gave us to be 6.67 times 10 to the power of minus 11 Newton meter square per kilogram square. So to solve this, we'll use that Newton's gravitational law, or Newton's law of universal gravitation. So the formula is F is equal to G bracket open, M1, M2 bracket close, all over squared. So this is the formula. So we'll now be using that formula to solve this. So the parameter they gave us, they are looking for F. They gave us our G, they gave us our M1, they gave us our M2, they gave us our R. So putting them in all together, we would see that solving it here, you'll be having our G times 5.5 times 10 all over the square of 2. When you solve this thing, if you press your calculator and solve this, you'll be getting your final answer to be 8.3375 times 10 to the power of 10. 10 to the power of minus 10. So I just hope that this is clean for everybody. I also hope that this is going to be clean for everybody.
It is, sir.
Okay, so then I hope there's no question, or does anybody have any question? Let me answer the question.
Wait, you.
Okay.
Hello, sir.
Yeah, I can hear you.
The radius is given,
Yeah.
but from the question is radius square.
The formula. The formula is radius
From the
square.
formula is radius square. So we have to square the
Yes.
20.
Yes. It's not necessarily radius, so it's not really radius. It's distance between both of them. It's
Okay.
distance between both. So
Okay, it's
don't mistake it.
represented with R.
Yes, it's represented with R.
But
Yeah,
hello,
I can
sir.
listen. I'm hearing. Yeah, I'm listening.
But, what if in a situation where the R square is given? R square is given, not R. We don't need to square.
If they give you R square, that means you don't need to square the R again now. You just put it under. Let us say they say R square is 4. You just put it as 4 there as the denominator.
Okay.
So hope we are good to go.
Yes, sir.
Okay. So let's move on to our next slide. So now importance of
Sir, please wait.
importance. Okay.
Sir, I can't see your screen.
Sorry, I don't know. Can you see it now?
No.
I think can other people see my screen?
Yes, I
I
can
can
see.
see.
I'm seeing it. I'm seeing
Cannot
it.
see.
I think probably it's your network at your end. I don't know. I cannot help with that one. I don't know.
So you can continue.
Okay. So let's go on. So the importance and the derivation of this Newton's law. So now this law is used to derive the weight of the Earth. We know that generally there is a formula that says that the normal formula for weight is equal to mass times acceleration due to gravity. Sorry, mass times acceleration, that is what weight is. Mass acceleration, but for objects in the Earth, it's mass acceleration due to gravity. That's how you used to get the weight. So now, from this weight is also the same thing as the force most of the times. It's almost the same thing as the force most of the time. So now they can use this formula now to get the what they call it, the acceleration of the Earth by equating this formula to the other formula that we have here, making mg, that's mg. Instead of f here, we now have mg on this side, where one of the m is m1. So if you cancel out if m cancel out m1, you would then be having g equals to capital G m2 all over r2 squared. So this formula is used to predict the mass of the mass of the Earth, and can also be used to get the acceleration due to gravity. So this is the formula that is this Newton's law that they use to determine the theoretical acceleration due to gravity, and also the weight of the Earth. So the force of gravity, the gravitational force is equal to the weight of the Earth. The gravitational force that they can calculate is always equal to the weight of the Earth. And that gravitational force, the formula F is equal to W, because force mostly is always equal to weight. Force is mass acceleration. Weight is equal to mass acceleration, but now due to gravity. So if both of them is force is equal to mass acceleration, weight is equal to mass acceleration due to gravity. So you can equate both of them together. And when you equate both of them now, you will then be having mg equal to, this is our first formula here. This is our g m1 m2 over r squared. So one of the g will cancel out one of the m on the other side, and we'll then be having g, which is acceleration due to gravity, equal to g m all over r squared. That's what we have here. So this is one of the importance of this formula. It helps to get the theoretical acceleration. Okay, on your paper, write the formula, this Newton's formula. This Newton formula that we have here, write F is equal to G bracket open m1 m2 bracket close all over r squared. Write it on your paper. Then on the second side, also write W is equal to mg squared. No, W is equal to mg. W is equal to mg. Then now under now write, we know that force is equal to weight. We know that force is equal to weight. We know that force is equal to weight. Therefore, we will take this side of force, this part of force formula, the G m1 m2 all over r2, and make it equal to mg. But now the G on this mg is not capital G, it's m small g. Or you can flip it on both sides where it will be mg is equal to gm1 m2 all over r2 is still the same thing. So now one of the m will cancel one of the m in the other formula. So our g will now be equal to gm all over r squared. So that's what I'm just trying to say. I don't know whether it's clear now.
Anyone, M1 and
will cancel.
M2, I can cancel any.
Yeah, just cancel one of them. But when you cancel one of them out, the m will now change to capital M, because now that m, we are assuming that m is the mass of the Earth. The m that you cannot cancel out is the mass of the Earth.
I don't understand.
M1, M2. Just cancel one m. Then now if you cancel m1, instead of you writing gm2 all over r squared, just write g capital M all over r squared. You get
What of
where they're saying that
the small g with the m I cancelled?
Yeah, the g will be, that small g will now be equal to the capital G m all over r squared. Is that not what it gave you?
And that is force of gravity, Abi.
That's now acceleration due to gravity. That small g is acceleration due to gravity.
Okay.
Yes, acceleration due to gravity is now equal to the gravitational constant times that m that is remaining all over r squared.
You know how to teach you. I've gotten it right.
Thank you, ma.
Thank you, sir.
So now, that's for this one now. That's for this one. That's what the implication of, that's the importance of this formula. It can help us to actually calculate theoretically the acceleration due to gravity. As mean we were doing a practical session, or maybe I had this thing, an illustrator now. As mean I was using my device, not my phone, I would have been able to show you what I meant. So, but for the sake of what we have here, we'll just move forward. So now this now is we said what?
That it can help us to calculate theoretically the what?
Yeah, the acceleration due to gravity. So now let's move on to gravitational potential. Gravitational potential, this is another topic under gravity. So now, the gravitational potential is defined as the work done per unit mass in bringing a mass from infinity to a point. Gravitational potential is the work done per unit mass in bringing a mass from infinity to a point.
Per unit
so
what?
The formula per unit mass is the work done per unit mass in bringing a mass from infinity to a point. In bringing a mass from infinity to a point. So that's what gravitational potential is. It's just like I said, you're trying to say in the case of gravity now, it is now work done. Like the work done under gravity now is what they're talking about, is what they call gravitational potential. In normal thermodynamics, they'll call work done. In normal mechanics, they'll call work done. But in terms of gravity now, they'll call work done gravitational potential.
Okay, it's not called work done, but gravitational potential.
Yes. So per unit mass, yes, just gravitational potential per unit mass. That's just how it is called now. So now we have our example here, seeing how the questions come out under gravitational potential. So these are the question comes out to say calculate the gravitational potential at a point 4 times 10 to the power of 6 meters from the center of the Earth. They're giving us distance between the object and the Earth. They're giving us our R. So now the question is now trying to tell us that we should find the gravitational potential. Now they're asking us to find from this question. So we find gravitational potential. So now the mass of the Earth, write this one in your notes now. The mass of the Earth is always constant, and the mass of the Earth is known to be 6 times 10 raised to power 24, not minus 24. 6 times 10 raised to power 24 kilograms. 6 times 10 raised to power 24 kilograms. That is the mass of our Earth. That's the mass of our Earth. It is more than trillion kilograms. Is more than that. 6 times 10 raised power 24 kilogram. So that's the mass of the Earth. So anywhere you ask you for the mass of the Earth, it's always constant. It's not changing. So though in some
Mass
places
of
I might
the
see,
earth.
yes, mass of
Mass
the
of
Earth.
the earth.
Yes, mass of the Earth is 6 times 10 to the power of 24 kilogram. So now we're not trying to use that formula to calculate the gravitational potential. The formula for gravitational potential is V, representing gravitational potential, is equal to minus G, that is gravitational constant, times M, that is mass of the Earth, all over R. That's the formula we have up here. This V is equal to minus Gm all over R. So that's the formula for gravitational potential. So now from this question, they're giving us our R to be 4 times 10 raised power 6. They gave us our R to be 4 million meters. That is 4 times 10 raised power 6 meters. So now with that, now we can get the gravitational potential by applying this formula. We know our G, our capital G, as our gravitational constant, which is 6.67 times 10 power of minus 11. We know our capital M, which is the mass of the Earth, which is 6 times 10 raised power 24. Then we know the R now. This is not R square. For this gravitational potential, it's not R square, it's just R. So take note so you don't make that mistake. It's just R, and the formula is minus Gm all over R. So now, imputing those things inside the formula, you'll be having here minus gravitational constant times mass of the Earth all over the distance. If you solve it, your final answer will be giving you 10 minus 10 times 10 to the power of 7 minus 10 times 10 to the power of 7, or minus 1 times 10 to the power of 8. So that will be your final answer if you round it up in standard form. So the final answer will be minus 10 times 10 raised power 7, or 1 minus 1 times 10 to the power of 8.